All right, so let's get started. So in this tutorial, we will be covering exercise 10.1, 10.2, 10.3, and 10.4. So from exercise 10.1 and 10.4, there are some questions. Most of the questions are not covered. So that leave us with a very small exercise for exercise 10.1 and 10.4. So let me just share my screen and show you. Okay. All right, so let me know if the screen is coming through.
Yeah, it's good.
Okay. All right, so so the first question is basically regarding the graph. So this exercise 10.1 is based on the graph. So the first question is question 11. It's on page number 683 of your textbook. So question number 11, so let G be a simple graph. Show that the relation R on the set of vertices of G such that U R relation V, if and only if there is an edge associated to UV, is a symmetric, irreflexive relation on G. So here we have if URV, so we already have the URV. So if URV, then there is an edge associated with UV, let's say UV, but UV equals to VU, right? So UV equals to VU. So this edge is associated with VU. And therefore we also have that reverse relation, which is VR relation U, okay? Thus we can conclude, thus by definition of this, by definition, R is a symmetric relation because we can write it the other way around as well, symmetric. R is a symmetric relation, okay? So a simple graph, so what is a simple graph? So a simple graph is a graph which does not allow loops. So a simple graph doesn't allow loops. Therefore, URV never folds. And so by definition, R is irreflexive. Therefore, we have shown that URV is the relation URV holds if and only if there is an edge associated to UV is a symmetric irreflexive relation on G. Okay, so we had that URV relation, and we're saying if URV is true, then there is an edge associated with U going to V. But we also know that UV equals to VU. So therefore we can say that there is an edge from V going to U. So therefore V are U. So we can say that this is a symmetric relation. And because it's a simple graph, it does not allow loops. Therefore it's R is irreflexive by definition. Question? All right, no question. Let's move on to the next one. So, so as I mentioned earlier, so 10.1 is very small. So there are very limited questions we are taking from this exercise. So this was the only question that from this exercise. Let's move on to exercise 10.2. So 10.2 is also regarding the graphs. So we have the bipartite graphs, matching graphs, special kind of graphs. So all in this exercise. So let's take the first question. So in exercises 1 to 3, find the number of vertices, the number of edges and degrees of each vertex in the given undirected graph. Identify all isolated and dependent vertices. Okay, all right. Okay, let's take number 1. All right. So for question number 1, we would say that it has a number of vertices. Number of vertices equals, number of vertices are basically 6. 1, 2, 3, 4, 5, 6, A, B, C, D, E. Okay. The number of vertices are 6, and the number of edges are equals to, so we just count the edges, 1, 2, 3, 4, 5, 6. So they're all 6. Okay. So now let's calculate the degree for each vertex. So degree for A is, so let's see. So we have the 2 edges out of A. So the degree will be 2. Degree for B vertex. So for B vertex, we have 4 edges coming out of it. So therefore the degree for vertex B will be 4. So let's talk about degree of vertex C. So for C, we have just 1. So therefore degree is 1. Okay. Just make it short here. Okay, so degree. Right. So degree of D equals to, now the D, it doesn't have any edges coming in and out of it. So therefore the degree will be 0. Degree E, so for E, we have 2 edges. So therefore degree is 2. Degree of F, so for degree F, we have 1, 2, 3 edges. So therefore the degree is 3. Okay, pretty straightforward. No big logic. Let's take another one of this. Let's talk about question number 3. Okay, so this is the question number 3. Just maximize a little bit. So here the question number 3. So we talk about the number of vertices. So the number of vertices are, so we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8.
Sorry, is this supposed to be 9?
Yes, so there is also an F here. But this was like a very off the question. So yeah, pretty good catch, thank you. So the number of vertices are 9. Number of edges. So number of edges will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So the number of edges will be 12. And bring up the screen. Okay. Maybe I can bring this up and that one down. Okay. All right. So number of edges are 3. Okay. So I'll just take this. A, B, C, D, E, F, G, H, I. So A, B, C, D, E, F, G, H, I, and then just all right. So the degree for vertex A is 3 because it has 3 edges. Degree for B will be 2 because it has 2 edges. Degree of C will be 4 because it has 1, 2, 3, 4 edges. Degree of D will be 0 because it does not have any edges. Degree of E will be 1, 2, 3, 4, 5, 6. Degree of F will be 0 again, no edges. Degree of G, we have 1, 2, 3, 4. Degree of H will be 2 only, and then I will be degree of I will 1, 2, 3. Okay. So this is like the number of vertices, number of edges, and the degrees for each vertex for this graph. Pretty straightforward. No big logic. Any question here? All right, no question. Let's move on to the next one. Let me just change the order back. Okay, so in this question, 7 to 9, we have also to determine the number of vertices and edges and find the in degree and out degree of each vertex for the given directed multigraph. So now, previously we have an undirected graph, but now we have a directed graph. So therefore it will also have an in degree and out degree for each vertex. Okay, so let's do this. Let's take question number 7. So let's only do, let's take the first 7. Okay, I'll just put on the next page. Okay. So for question number 7, okay. So number of vertices, we already know. So 1, 2, 3, 4, the number of vertices are 4. Number of edges. So number of edges, we have to say 1, 2, 3, 4, 5, 6, 7. So it doesn't matter whether it's an inward edge or an outward edge. So we're just counting them. So the number of edges are 7. Okay. Now let's say the degree of A. We have to count the degree of A. And then this plus sign here indicates the inwards degree, the outgoing degree from it, right? So the outward direction arrow from away from it. Okay. So degree of A is 1, right? So this is the outgoing. Okay. So I'll just put it as a reference. Plus outgoing. And the degree of A negative, it basically is 0 because it is basically incoming is 3 because it has 1, 2, 3 arrows coming into it, right? So therefore the degree is 3 incoming. So negative means incoming. Okay. Likewise for B, so degree of B positive 2, and then I'll just copy and paste this for simplicity. B negative. And then I'll do for C and D as well. C and D. So this will be C, C, D, D. Okay. All right. So B outgoing edges. So edges going out of B here. So we have one edge going out of B, and then we have another edge going out of B. So therefore the degree B is 2.
So can I ask a question?
Yeah.
Is positive always coming out?
So positive is basically, it means that it's outgoing, right? So it's basically directed away from that vertex.
Oh, okay. Oh,
yeah.
I see. Okay.
And then this, yes, and then this negative is the edge coming into that vertex, right? So you see that there are arrows. So it basically tells the direction. So a degree of B negative, the incoming degree for B. So we have only one edge coming into B, so therefore it's 1. Degree of C positive, that is outgoing. So we have one C that is outgoing. Degree of C that is incoming, we have 1, 2 coming to C, therefore it's 2. Degree of C outgoing, degree of D outgoing, so we have 1, 2, 3 degree of D outgoing. And then for degree of D that is incoming is only 1, right? So therefore negative. Okay. Right, let's take another example. Question number 9. So the 9, for question number 9, so we have number of vertices first of all. So number of vertices, as we know, we have number of vertices as 4. Oh, sorry, 5. 1, 2, 3, 4, 5. It's so easy to miss this long one. It seems like a dot. So number of edges we have is, so we just count the edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. The number of edges are 13. Okay. So let's calculate the degrees now. I'll just copy and paste this. So just take. All right, so degree for A that is outgoing. So we have how many edges going out of A? So we have just one edge going out of A, right? So that therefore it's 1. And then degree of A incoming. So edges coming to A, 1, 2, 3, 4, 5, 6 edges coming to A. Therefore we have this. So we have a degree of B that is outgoing. So a number of edges going away from B, 1, 2, 3, 4, 5. 5. Degree of B incoming edges is just only 1. For C, we have the degree as the outgoing is 5 and the incoming is 2. We have for D, we have the outgoing as 2 and the incoming as 4. And we also have E here. So DE equals to, now here E is an isolated node, so therefore we don't have any edges coming in and out of it. So therefore the degree is of E positive is 0. Likewise for E negative, it's also going to be 0. I'll just switch the order. Any questions? All right, if no question, let's move on to the next one. So we have the next exercise, which is exercise 10.3. So let's take the first question from this exercise. So basically what we have here in this exercise, we sort of have to draw the adjacency lists here. So adjacency list basically tells like what are the adjacent vertices of a given vertex. So I have already basically solved it for you just to save some time. So we have this question number 1 here. We have to find the adjacency list. So I'll just make it a little bit shorter so that we fit this here. Okay. So here we have 4 vertices, as we know. So for vertex A, we have the adjacency vertices as B, C, and D because it has the edge going to B, C, and D, right? For B, we had the edges at A and B because it has edge to only A and D, right? And not to C. So for C, we have the adjacency as A and D, right? So C only has edge to A and D, therefore A and D only. And D has an edge to A, B, and C, all of them. So therefore the adjacency list counts to this. Let's take one example of a directed graph. So for the directed graph, let me just all right, so here, question number 3. So in this question A, so this is a directed graph, so we should be careful about the adjacency vertices. A vertex can be adjacent to itself as well. So therefore, because of these loops. So here we have the vertex A. So now it's adjacent to itself as well. This must be noted that it is adjacent to itself because there is a loop that is going inside of it as well. So now that there is a loop inside of going it as well, so we can include A itself we have the edge to B, C, and D from A. So therefore, the adjacent vertices are this. For B, however, the only adjacent is D because it only has one incoming edge from D. Therefore, it's only adjacent to D and not from A because it doesn't have an arrow going out of A. So likewise for C, we have A and then B. So we have the arrow going away to A and B. Therefore, the adjacents are A and B. For vertex D, we have the adjacent vertices D, B, and C because for D, we have a loop. Therefore, we include itself, the vertex itself, and then we have the B, the loop, the arrow going to B, and then we have the arrow going to C. Therefore, they're adjacent. Okay, so the directed graph basically is a little bit trickier to find the adjacency list, but of course the concept is very simple. So once you know the concept, you can do it no problem. Any questions? All right, if no question, let's move on to the next one. So basically we have we have to convert the adjacency list into adjacency matrix now. So what we do is, so we have this question number 3. I'll just take it and put it here. Okay. So we have this adjacency list. We have to convert it into adjacency matrix now. So the way we do it is basically we have like the number of vertices. So it creates like a square matrix. So in a square matrix, we have the length and the height same. So here we have A, B, C, D columns, so representing the vertices. And likewise, we have A, B, likewise, we have A, B, C, and D here as well. Okay, so we put here 1 because A is adjacent to itself. We put 1 here because A is adjacent to B, and A is adjacent to C and D. So therefore all are 1, right? So because A is adjacent to A, B, C, D. Now we put 0 here because B is not adjacent to A and B is not adjacent to B itself. C, it's only adjacent to D, right? So therefore we put 1 because it's only adjacent to D here. Now for vertex C, we have A because it's adjacent to vertex A, so therefore we put 1. It's adjacent to vertex B, we put 1. It's not adjacent to C or D, therefore we put 0. Okay, and likewise for vertex D, it's not adjacent to A, but adjacent to other ones, so therefore we put 0 for A, but 1 for the other ones. So the question is, are the rows, the vertex and column adjacent vertices? Are the rows, the vertex and columns the adjacent vertices? I'm not sure if I understood the question correctly. So
the rows, right? The first row is 1, 1, 1, 1. Is that representing A, B, C, D?
Yes, so that is representing A, B, C, D. So like here, so we have this adjacent vertices. So A, B, C, D. So you can imagine A, like, so this here will represent A, this represent B, this represent C, D, this represent D. And likewise, this will also represent A. We put only 1 in place where it is basically adjacent to that particular node. So here we put 1 because A is adjacent to A, right? So A is adjacent to A. So therefore we put 1. Otherwise we put 0.
Okay, that makes sense. Thank you.
All right, let's move on to the next one. So for question number 19, so we pretty much have to do the similar thing. We have to just find the adjacency matrix of the given directed multigraph with respect to the vertices listed in alphabetic order. So as just like the previous one, so it's not a big logic here. So it's pretty much similar to what we have done before. So here, so let's take question number 19 here. So we have, as you can see here, so I have created this matrix. On top of it, I am just writing it for my reference. So it's A, so this column representing A, this one B, C, and D. Likewise, this row first is represented with A, B, C, and D. Okay, so now we put, sorry, just give me a minute. All right, sorry. Yeah, so here we first see that is A adjacent to A. So we see that there is no loop. Therefore, we cannot say that A is adjacent to A. So therefore, we put 0 here. Now we see is B adjacent to A or not? Now we see that there is an edge which is going out from A to B. Therefore, we know that B is adjacent. So we put 1 there. Now we check for C. Does A have an edge going from A to C? It does not. So therefore we put 0 here. So for D, we see, does A have an edge going from A to D? It does not. Therefore we put 0 here. Likewise for B, is B adjacent to A? So here we see, does B have an edge going from B to A? It does not have any edge. Therefore, we can say that this is 0 here. We put 0. Now, is B adjacent to itself? Yeah, because it has a loop here. So therefore, we know that the B is adjacent to itself. We put 1. To know is C adjacent to B, we see if B has an edge going from B to C. So we see that there is an edge going from B to C. Therefore, we can say that it is. We put 1 here, and then we say for B to D, does B have an edge going from B to D? It does not. Therefore, we put 0. And likewise, we fill out this matrix, remaining matrix, with this simple concept. Okay, any question? Let's do another one. Question number 21. So I'll just take this and put it here. So for question number 21, we have a lot of edges we can already see. So a degree can also, the number of edges can also be more than 1. So therefore, it's not either 0 or 1. It can be also be 2, 3, or 4. So here we have the number of vertices written on the top, A, B, C, D, and likewise we have A, B, C, D representing these rows. So if we see for A vertex, it has an edge going into itself. So therefore A is adjacent to itself, right? So therefore we put 1 here. Now for B, is B adjacent to A? So we see that there is an edge from A to B. Therefore we put 1 here. for C, we see that there are two edges going from A to C. Therefore, the adjacency matrix will have two for at this place. So there is this D as well here. So we have an edge from A to D. So therefore we put 1 here. So for B, does B have an edge going to A? So it does have an edge going to A. So therefore we put 1 here. So here we have, does B have an edge going to itself? So because B does not have edge going to itself, therefore the adjacency matrix will have 0 for this. We have, does B have an edge going from B to C? So we see this B, and then we see this C. Because it does not have any edge going from B to C, therefore we put 0 in its place.
Could I ask a quick question?
Yes.
Under C, why is it 2?
On this one here?
Yeah, but yeah.
Yeah, so basically we see that, so this one basically here, it says that does A have an edge from A to C? Is there an edge from A to C? So we see that there are two edges going from A to C, right? So these two edges, directed edges going from A to C. So this one and this one.
Okay.
Therefore we put 2 here. Likewise, for this one here, we have two edges going from B to D. So this one and this one, we put 2 here.
Okay. What about what about B? For 2, B bottom 2.
This one, yeah. So here we have two edges going from D to B. So from D to B. So we have two edges going from D to B. So this one and this one. Therefore, we put 2 here.
How do you know? Why are you checking if it's going from D to B in this case?
So here we have this adjacency matrix. Basically, we fill this out in a way that it sort of covers all the orientations. So we have here, so for example, this row here, this one, the last one here, it represents the vertex D. So it's basically the—
Oh, okay. Okay,
yeah.
vertex. Okay.
Yeah, so it's—
and then, so it's like a 4x4 matrix. So the first row is A, the second row is B, C, and then D.
Exactly, yeah.
And then you look. Okay, that's okay. That makes more sense. And this is 10.2, right?
This is 10.3.
Oh, okay. Okay, my bad. Okay, thank you.
Yeah. Okay, so yeah, so when we don't have any edge, so for example, this 0 comes in because we don't have any edge going from D to A. So therefore, this is 0. So we put 0 where when there is no edge going, we put 1 when there is one edge going, and if there are two edges going, we put 2, and likewise we do it for the other ones. Okay, so pretty simple question, pretty simple concept. Any questions here? All right, if no question, let's move on to exercise 10.4. So from exercise 10.4, we are also taking very limited questions because there are a lot of concepts that we are not dealing in this course. So we have the paths and isomorphism here. So we won't be covering the isomorphism. So we'll be covering paths a little bit. So what we have to do is we have to basically determine the path, right? So the first question is, does each of these list of vertices form a path in the following graph? Which paths are simple? Which are circuits? What are the length of those paths? So if it's a path, we have to basically tell its length. And then we have to say if it's a simple or a circuit. Okay, so let's say we have this path A. So we have this path A for question number part A. Okay. So for question number A, we have A, E, B, C, B. Is there a path from A to E? There is a path from A to E, so we take this path. Is there a path from E to B? So we take this path. Is there a path from B to C and then back to B? Yes, there is a path. So we say that there is a path. There is a path. So I can take this path and come back to that node. So now what about the length of this path? So length is, so the length is, so we take A to E, so that is length 1, E to B, that is length 2, B to C is length 3, and C to B is length 4. So therefore length is 4. So is this a simple path? It's not a simple path because it's not, basically it's not going from one direction to another direction, right? So it's going backward and forward. So we went from B to C and then we come from C to B back, okay? So not simple. And is there a circuit in the path? So there is not a circuit, it's not a circuit path. Let's take part B. So part B, we have A to E. Is there a path from A to E? Yes, there is. And then we go from E to A, and then A to D, D to B, B to C. And then I cannot go from C to A back now because for that I need to take another node. So therefore, this is not a path. Part C. So for part C, we have E to B. So we take path from E to B, and then we go to A, because now we cannot go directly to A, right? So because it's not adjacent to A. Therefore, we will say that this is not a path either. Take part C. So we have this starting node as C. So we start at C, and then we go to the node B. Then from B, we went to the node D. Then from D, we went to the node A. And then we went to E, and then we get back to C. Now we see that there is a path. So there is a path. What about the length of the path? So what is the length? So length is basically, we went from C to B, that is length 1. Then from B to D, that is length 2. Then to A, that is length 3. Then to E, that is length 4. And then to C, last node. So that is length 5. So the length is basically for this traversal is 5. Now, is there a circuit in the path? So we see that there is a circuit in the path. So circuit, it basically means that, so it started from the node C and it ended on the node C or the vertex C. Therefore, we say that this sort of formed a loop, right? So it ended where it began. So therefore, there is a circuit in the path.
Also, can you clarify why this is a circuit and why A is not a circuit? Can you explain why D is a circuit? What's the difference between A and D?
Right. So here in part D, so we started with the node C, right? So we started with node C and we ended on node C.
Right.
Therefore, this is a circuit. But because in part A, we started with node A, we did not end it in node A, right?
Okay, there's no loop. Okay.
So therefore, this is not a circuit.
Okay. Okay.
Yeah. Any other questions?
Can you go back to 10.1? I kind of came late.
10.1?
Yeah.
Which question are you looking for?
Wait, is this part of 10.1?
Yes.
Question 11?
Yeah, so question number 11 is a part of 10.1. Let me just verify that quickly.
I think this is, oh no, it's not that.
Let me just verify that. Yeah, so for 10.1, yeah, so we have question number 11 included. So the questions that are not included are basically, so this one. So for 10.1, we don't cover question number 1, 2, and
okay.
from 13 to 38.
Okay, thank you. That's it. Okay, thank you.
Okay. Erin, do you have any specific question from this exercise?
Actually, no.
Okay. All right, so let's move on to the next question. So we have this question number 15. So we have to basically find the strongly connected components of each of these graphs. Let's do part A. So for question number A, we have the strongly connected components. So we see that, so we, if we take the node A, we have an edge going to B, and then there is an edge going from B back to A. And then likewise for this F as well, right? So I can always come back to where I start. So from A, I can go to B and come back to A. I can go to F and I can come back to A, okay? So we say that the strongly connected component is this one set here, ABF, because it's sort of from a loop, and we can come back to where we started. Next one, the other strongly connected component will be, so if we take a look at this one here, so we started at node C. So from C, I can go to D, and then I can go to E, and then I can come back to this part here. So this is a strongly connected component as well, right? So I can go and come back to the same node. So I will say the C, D, and E will be like the strongly connected components. Or let's take another example. Part number B. So for part number B, we have a couple of them. So if we take part B, we can basically, if we take this node F, let's say, and we will see that if we take node F, we can traverse to each node in the in the, if we take this node F, we can traverse from this node F to every other vertex. So therefore, just this vertex itself is very strongly connected. Likewise, if we take this vertex G here, so we will see that this part here is not very strongly connected, because if we start at G, we won't be able to go anywhere, right? So therefore, we'll do this G as well. So the remaining ones are A, B, C, D, E, and H. So these ones are strongly connected. So let's take the last one as well. So for question number C, if we take the node here, this C, right? So we see that this C node here, if we take that, this is strongly connected, right? Because this is strongly connected, it is very important. A lot of nodes are ending at this node, right? So they need C. There's no outgoing edge out of C. So therefore, this node is very important and strongly connected. And then we basically will have the rest of the A, B, D, E, F, G, H.
I have a question. Can we separate the elements into sets on their own? What I mean, like element C and then in a set, and then A in a set on its own. Can we do that or no?
Not really. We cannot do that.
Because I was thinking that D can also be a strong component. So I was thinking that D can be in its own set.
So D cannot be a strong component because so we can still traverse to D, let's say, because it has an outgoing edge, right? So it has an outgoing edge from D to B, and then it has also from D to E, right? So we can traverse from D to the other nodes as well. So therefore, this is not a strongly connected one.
Okay, makes sense. Okay. Yeah, it makes sense now. Okay.
Yep. Right. Any other questions? All right, if no more questions, then this is pretty much it for this tutorial. So this tutorial covered from exercise 10.1, 10.2, 10.3, and 10.4. So there were very limited questions that we took from exercise 10.1 and 10.4. Our main focus was on 10.2 and 10.3. So make sure to try those out. And if you guys have no other questions, then that'll be it for this tutorial, and I'll see you guys in the next one. All right, take care guys, and bye now.